Okay, in this problem we're going to review doing utility maximization problems and doing it in the context of trying to determine the income and substitution effects of a price change. When you do this, you're going to be doing 3 problems and then analyzing and kind of comparing what these 3 problems tell you about how much of the decrease in consumption of something is due to them feeling poorer, that's the income effect, and how much of it is due to the price change affecting the opportunity costs between the 2 goods. That's the substitution effect. So we're going to have 3 different solutions. Problem A here is what we could call the original solution. How much X and Y would this person buy at the current prices? Here we have X is $10, Y is $10, and they have a budget of $200. So this is the original solution. We'll call that solution A. And then the price of one of these 2 goods is going to go up or down. And in this case, what's going to happen is the price of X is going to go up to 20. And then we're going to do solution B. We could call this the after the price change solution. Then after that, we're going to do the hypothetical solution. We want to know in this case, how do we get this person back to their old utility level at the new prices? So we're going to be using the prices from problem B, but the utility level from problem A. Let's dive in. So we want to set up our 2 equations and 2 unknowns. And equation 1 says set the marginal rate of substitution equal to the price of X over the price of Y. The slope of an indifference curve is the MRS. The slope of the budget line is the price of X over the price of Y. Now both of these are negative, so we're going to ignore the negative sign since they're just going to cancel out anyway. Now we're going to use the shortcut trick to finding marginal rate of substitution. You could do the derivative with respect to X, divide it by the partial derivative with respect to Y, but we'll just use our shortcut trick, which says take the exponent on the X, which is 0.6, multiply it times Y. Take the exponent on the Y, which is 0.4, times X, and that's a function for marginal rate of substitution for a Cobb-Douglas utility function. Set that equal to the ratio of the prices, 10 over 10. And then usually what I like to do is just simplify this a little bit on the fly here. So 0.6 over 0.4 is the same as 3 over 2, or we could write it this way, 1.5 y over x equals, and then the 10 over 10 is just 1. We want to solve this equation for y or x and then plug it in to the budget line equation. Let's just go ahead and solve this for y, since that's kind of the rhythm I like to get into. So we have 1.5 y equals x. Y equals 1 over 1.5x, so that's going to be 2/3 x here. And if you wanted to write that as 0.66 or 0.67x, that's fine as well. Now, so we can call that equation 1, sort of simplified. Equation 2 is our budget line equation here. Price of x times x, so 10x plus price of y, 10 times y, has to equal our budget. That's $200. Now what we want to do is plug this, since y equals 2/3 x, plug that in there for y. And we get 10x plus 10 times 2/3 x equals 200. And when we simplify that, we're going to get 16.66666 or 16.67x equals 200, telling us that we should be getting about 12 x's. Now you get a little bit less, but if you didn't round at all and you kept that 2/3 throughout all the analysis, it would turn out to be exactly 12. Again, rounding a little bit, being slightly off is perfectly okay in these kinds of problems. Now, what we want to do is figure out how much y we would get. And then we want to take this, x equals 12, and plug it back into this equation. And that'll tell us how many y's we'd get. So what's 2/3 of 12? Should be 8. So y equals 8. The last thing we want to do is figure out how much utility this would get us. And now we want to plug x and y back into our utility function. So our utility function is x to the 0.6. So we get 12 to the 0.6 times 8 to the 0.4. And I'm getting something like 10.2. Now I'm going to write that 10.2 up here in this blank, because we're going to need that later on whenever we solve problem number 3 down here, or problem C, we'll call it. Now before we do anything else, let's go graph all of this to make sure that it looks right. So down here at the bottom of this handout, we have a set of indifference curves, an indifference curve map here. And this first budget line is going to be with $200. We're putting x on the x-axis, of course, and y on the y-axis as usual. We want to graph the budget line, and with $200 and x's cost $10 a piece, I could afford 20 x's at most. And since y's are also $10, that's going to be the same here. And if we connect those with a straight line, we're going to have our budget line. And now our solution we got was 8 y's and 12 x's. And so let's graph this on 12 x's and 8 y's. And we want to make sure, number one, that this is a point on the budget line. Number two, we want to make sure that it's a point where it looks like the slope of the budget line, the red, is equal to the slope of an indifference curve that's nearby. And here we have this light gray indifference curve that looks like it's nearby. And yeah, the slope of that indifference curve, if we zoom in there, it looks like it's about the same slope. Now our point looks like on our budget line is going to be a little bit beyond this gray indifference curve. If we look at the legend, the gray indifference curve is for 10 utils, and that means that at this point A, this person should be able to get a little more than 10 utils. And that's what we found. We found that this person should be able to get 10.2 utils by buying 8 y's and 12 x's. Everything looks good there. So that's problem A. Now the price is going to change of something. And so in this problem, the price of x is going to change to $20. Let's solve these problems again. So we have the marginal rate of substitution equals the price of x over the price of y. Now this marginal rate of substitution part, the 0.6y over the 0.4x, isn't going to change. That represents this person's preferences. And unless something about a problem says their preferences are changing, then we don't mess with that. So 0.6y over 0.4x. Or we already kind of simplified that before and said, well, that's the same thing as 1.5y over x. So why not take advantage of those simplifications? What's changing here is it's not the price of x and y being 10 over 10. Now it's the price of x is 20. The price of y is still 10. So we're going to set that equal to 20 over 10. And again, I like to go ahead and simplify that as I go. 20 over 10 is obviously the same thing as 2. And now we want to solve this for y. And that'll give us our equation 1. So we're going to have 1.5y equals 2x. Divide both sides by 1.5. And we're going to end up with y equals 1.33333x, or 4/3 x. So that's our equation 1. Equation 2 is just the budget line again. So the price of x is 20 now, times x, plus 10 times y, equals, we still have $200. And we're going to plug this y equals 1.33x in for y and see how much x. So when we do that, we're going to get 20x's plus 10 times 1.33, which is 13.3. So 13.3x equals 200. Add the x's together, we get 33.3, and that's really 33.3333333, right? So 33 and a third. X's equals 200. And when we solve that, we're going to get 6 for x. X equals 6. And again, if you round, you'll end up with something slightly different. But the exact answer we're going for here, if we left that as 33 and a third, would be 6 exactly. If you get 6.01 or 5.99, no problem. So here we have, if we plug that in here, we get y equals 1.33 times 6, and that gives us 8. So y equals 8. And again, we want to know how much utility this is going to give this person. So we plug in 6 and 8 into our original utility function, x to the 0.6 times y to the 0.4, and we should get something like 6.73. 6.73. So the story so far is, when the price of x and y are both 10, this person would buy 12 x's, 8 y's, and get a little over 10 utils in happiness, 10.2. When the price of x goes up to 20, then they're going to buy less x, only 6. They're going to buy the same amount of y, which is interesting. And this is a side effect. This is something that's a little strange about the Cobb-Douglas utility function. Is when the price of one of the goods goes up, it just always works out this way, that the amount of the other good doesn't change. So here, when the price of x goes up, the law of demand is going to work. You're going to buy less x, but you're going to buy the same amount of y as before. This isn't always realistic in all situations in the world. So this is kind of an assumption. If you're going to use a Cobb-Douglas utility function to model a situation, you are assuming, because you chose that kind of utility function, you're assuming that these two goods are not substitutes and they're not complements, that when the price of x goes up, you'll just buy less x, but you're not going to buy more or less y. So price of x goes up, buy less x, buy the same amount of y, but you're less happy. Your utility goes down. Now let's solve this decomposition basket. Now what we're doing here is saying, okay, suppose we were a benevolent dictator. Benevolent dictator means you're the ruler of a country and you see your people are being hurt and you're benevolent, you're nice, you're a good king. And you don't want your people to be hurt. You don't want them to be sad. So you say, my people, I'll give you some money. I want to make you whole. I want to make it to where you're not sadder. Your utility, I don't want your utility to go down from 10.2 to 6.73. How much money do I need to give you? That's what we're solving here. What is the cheapest way to get our people back to a utility level of 10.2, given the fact that the price of x has gone up? So here's the mantra to repeat to yourself. When we do this decomposition basket, we're using the new prices getting back to the old utility. New prices, old utility. New prices, old utility. So our two equations are, number one, we want to set the marginal rate of substitution equal to the ratio of the new prices. Second equation we're going to set up is this equation is going to guarantee that the amount of utility that our people get, okay, x to the 0.6 times y to the 0.4, we want that to be equal to their old utility level, 10.2. So that's our equation number 2 now. Why is that the second equation? Well, we can't use a budget line equation for our second equation as we have been, because one of the things we're asking the question about in part C here is, how much money does a person need to get back to the old utility at the new price levels? So since we don't know how much money that is, we can't use that as one of our equations. But that is something we'll find out later. So looking at this equation number 1, we see we want the new prices, the $20 divided by $10, and then we want the marginal rate of substitution. Wait a minute, we already have that, right? We have that right here. So what we're using as equation number 1 for the decomposition basket is exactly the same as equation number 1 for the second problem, problem B, the after the prices have changed problem. And so rather than starting from the beginning, what we can do is just use this relationship that we already found out right here. Y equals 1.33x. So equation 1, y equals 1.33x. That just saves you some time if you go ahead and just reuse that part from the second problem that we did. Now our second equation we already wrote down, but let's put it here. X to the 0.6, y to the 0.4 equals 10.2. So now what we want to do is take this, plug it in for y right here, and here's where you need to be a little careful. Take your x to the 0.6, and when you do this, I recommend putting what y is, 1.33x, in parentheses, and raising it to the power that y is raised to. Just trying to help you be careful and not goof up. One of the most common problems I see people run into when they do this kind of substitution in for y in this particular circumstance is they'll raise the x to the 0.4, but they'll forget to raise the 1.33 to the 0.4. Because what we want to do here is distribute that 0.4 to both of the parts. So we have x to the 0.6 times 1.33 to the 0.4 times x to the 0.4 equals 10.2. So now we want to collect those x's. We add the exponents, and so we're going to end up with x to the first power times whatever 1.33 to the 0.4 is. Well, let's do that. 1.33 to the 0.4 power. I'm getting about 1.121 if I round. So x times 1.121 equals 10.2. And now divide both sides by that 1.121, and our solution is x equals, I'm getting about 9.11. And then we're getting y, again we're plugging that 9.11 into the y equals 1.33x formula. So I'm getting about 12.12 for y. We know the utility level should be 10.2. That's what this second equation is guaranteeing here. Now, if you're unsure or you're worried that you might have done something wrong, then okay, plug these numbers back into the utility function and guarantee that you do indeed get 10.2 utils. But here's where we want to bring in that budget line idea again. We don't know the budget, but we want to use that idea to figure out the budget. So x's are $20, so $20 times x, x is 9.11, plus $10 for each y, and this says we're going to buy 12.12 y's, equals how much? And this is how much money do you need to buy those things? I'm getting an answer of about $303.40. And you and I might have rounded a little differently there, of course, but should get somewhere within a few pennies of that answer. So $303.40. And now we want to graph these final two solutions. So let's graph the budget line and the solution for problem B. Let's graph the budget line and the final solution for C here. And then we'll wrap everything up by giving an explanation. I've got a little paragraph here to kind of help you have a template so that you can explain to somebody what have we done and why and what does it all mean. All right, so let's go back to problem B. We had $200 and the price of X was 20, the price of Y was 10. So if we graph this budget line, let's see, I'll do this in purple here, then we're only going to be able to afford 10 X's if we spent all our money on X, as X's now cost $20. We could still afford 20 Y's though, and so this new budget line, it's got a steeper slope. Slope of 2, right? Minus 2, but so, and our solution we found said we were going to buy 6 X's and 8 Y's. Okay, so let's look at that point. If it's on the budget line, it guarantees that we can afford it. So that's good. Whew. And the utility we said we were going to get was between 6 and 7, close to 7. Now, if we look at our indifference curve map here, we have an indifference curve for 6, that's the yellow one. We have one for 8, that's the blue one. And so, yeah, I could believe that that point here would give us about, almost, but not quite 7 utils. And another visual thing we want to check here is, does it look like the slope of that budget line is about equal to the slope of a line that would be tangent to the indifference curves near it, around that point, right? So we see that the slopes look like they're about the same there, and if we kind of move up, right, to this blue one, what we're saying is there is going to be an indifference curve here for exactly 6.73 utils. It's just we didn't graph that one. And if we wanted to, we could sketch that in. I'll just kind of try to freehand something here so we can get an idea of about what that would look like. You don't have to do this on your own paper if you don't want to, but that's what we're talking about. There is an indifference curve for 6.73. We just don't have it. We can't plot all of them on any given graph. All right, and then we want to graph this hypothetical decomposition basket solution here. So what we want to do here is take this budget of $303 and figure out how much X could we afford if we had $303 and X cost $20. Let's see. Well, 303 divided by 20. Well, that's going to be about 15, right? So I'll do this in green. So about 15. And then $303 divided by 10. That's how many Y we could buy. That's going to be up here a little bit off of our graph, but not so much that it's that big of a deal. And now let's graph that hypothetical solution. It was about 9 X's. All right, so about right there. And about 12 Y's. Let's zoom in here to make sure that that looks like that's about right. Yeah, close enough. Maybe I could stand to move that point up just a little bit. That's point C. Now visually, let's look at the 3 solutions we have, and this will help us when we go to do the breakdown of the income and substitution effects. We're saying we started here at point A on the red budget line. And then going from A to B, the price of good X went up. So that's the good we're focusing on when we're talking about income and substitution effects. The good X. So when we move from A to B, the price is going up and we feel poorer. The whole point of this C solution is to break that entire change between A and B into two parts. Let me draw a little line here, and we'll do this another way in just a second. Let me draw a little line here between A and B. This is the total change, the total amount of difference in our consumption of good X. We went from buying 12 X's to 6 X's. All right, so let me draw this line over here separately. From 12 down to 6. So this is point A, this is point B. The decomposition basket is always going to give us an amount of X in between those two. In between how much we were buying before and after the price change. It's not necessarily going to be exactly in the middle. In this case, it's not exactly in the middle, but it's close-ish. It's not necessarily going to be anywhere close to the middle. That's just what we're finding in this case. So we see that this point C, if we drop a line down there, breaks that into two different parts. So we're moving from A to C and from C to B. And our goal is to figure out, you can memorize it if you want. I don't like memorizing things, but figure out which of these would we call the effect due to an income change, the income effect, and which of these would we call a substitution effect. Here's the key. Look at what's happening when we move from A to C. A to C, we're just rotating the budget line. What's the utility, though, for solution A? Well, the utility at A is 10.2. What's the utility at solution C? Also 10.2. When we move from solution A to C, does this person feel poorer? Do they feel worse off? And the answer is no. They don't feel poorer. The only thing that's really changing between A and C is the relative price of X and Y. And when the relative price of two goods, comparing the price of good X and good Y, when that ratio changes, that's going to cause you to substitute from one good to the other. So when we move from A to C, that's the substitution effect. If that doesn't convince you, let's look at the move from C to B. From C to B, we see we're moving from the green to the purple. What's happening with this budget line when we move from the green to the purple? It's a parallel shift. A parallel shift in a budget line means your income's changing, but the relative prices aren't. The slope of the budget line, which is price of X divided by the price of Y, since that slope's not changing, we're not looking at the substitution effect. All we're doing between point C and point B is we're taking money away from you. That's the income effect. Your income gets lower, ceteris paribus. So that's a way to remember which of these two parts is the income effect and which part is the substitution effect. When it's just rotating the budget line but the same indifference curve, that's the substitution effect. A parallel shift, that's the income effect. So if we finish our little graph over here, our solution for the decomposition basket was 9.11 x's, right? So these are all amounts of x here. We have 6, 12, this is point C. So as we said on the graph here, the move between A and C, that represents the substitution effect. Between C and B is the income effect. So to sum this up, what we want to know is, what's the total change in X? Well, the total change in X was 6. We used to buy 12, now we're buying 6. So we're buying 6 units less. We want to break that 6 into two different parts. This part is the substitution effect, 12 minus 9.11. That's 2.89. So 2.89 is the substitution effect, and the rest, 3.11, is the income effect. So we'd say that this person, when the price of X increased, they bought 6 fewer units of X as before, and 2.89 units less were because the relative prices changed. The opportunity cost of X's and Y's changed. And then 3.11 units of X was because they felt poorer, just due to an income kind of effect. You could also think about the income effect as telling us about how much less opportunity they have to buy things, how their opportunity set has decreased, moving from the red line to the purple line. You can't afford as much X and Y combined as you used to when the price of X goes up. So that's another way to think about what this income effect has to do with here. Now that we've done all the analysis, let's fill in everything into our story here. And you do this along with me and say it out loud as we go through. So originally, the income and prices were, originally the person's budget was $200, and the price of X was 10, and the price of Y was also 10. And what did this person buy? Well, they used to buy 12 X's and 8 Y's. Just doing a press release here. And their utility level was 10.2. That's how happy they were. But then, when the price of X went up to $20, the consumer purchased what? Only 6 X's and also 8 Y's. Again, we're not saying that's something that's always true for all people all the time, but with a Cobb-Douglas utility function, that's a weird side effect. You'll always see it. When the price of one good changes, the amount of the other one does not change at all. That's a way to check your answers, actually. And they got a new utility level of how much? Only 6.73. So we discovered that at those new prices, an income level of how much could give them their old utility level of 10.2 back again. Right, $303.40. Our benevolent dictator, our benevolent king, if he could figure out all the information he needed, he could figure out how much more money he needed to give them so that his people weren't saddened by this price change. And then at that decomposition basket, that hypothetical solution, the consumer would buy 9.11 X's and 12.12 Y's at those new prices with this higher income. We found that the substitution effect of the price change in X is the move from the original, how much X? 12, right? To the decomposition basket, which was the 9.11. The income effect is the change from the 9.11 in the decomposition basket to the, how many? 6 units of X in the final basket. And finally, we learned we could compensate this consumer for the price change by changing their budget by how much. In other words, this last question is saying, how much money would the king have to give this person to get them back to their old utility level? This is what we call the compensating variation. Compensating variation. Compensating variation is how much money you would need to give someone to get them back to the old utility level. Well, in this case, we would have to take the person from their old budget of $200 up to a budget of $303.40. So the compensating variation is how much more money we'd have to give them. In the word compensating variation, the word variation just means change in the budget. Compensating means how much money. Compensating variation, and that would be, looks like $103.40. So $103.40 is how much we'd have to change their budget by to get them back to the old utility level. Compensating variation. On the next part of this handout, I have another problem where instead of the price of a good going up, we have a price of a good going down. This is a good one to think about doing. I'll post along with this handout, I'll put answers to this question so that you can check your work. But let me walk you through the idea here. Since the price of Y is going to go down, right? So here we're starting with the price of Y as 10. The price of Y is going to go down to 5. The question we're asking is a little bit backwards from what we did before. When the price of Y goes down, they're going to buy more Y. And we're asking, why are they buying more Y? What part of it is it because they feel richer? And what part of it is because the relative opportunity cost between X and Y changed? The slope of the budget line changed. And then when we get down here to the decomposition basket, what we're asking is, what's the cheapest way to get them back to the old lower utility, right? When the price of Y goes down, their utility is going to go up. This decomposition basket, we're going to try to get them back to the old lower utility level. And so this is going to require taking money from this person. Seems a little weird to think about, but that's what we're trying to do. In a way, we're trying to measure how much better off are they because the price went down, or how much income could we take from them to get them back to the old utility level. That's a way of measuring how much better off they are because price went down. And then the compensating variation in this case is going to be negative, meaning we're going to be taking money from them to get them back to their old utility level. Work on this. Again, I'll post the answers here in the last page of this handout so that you can check your work. And if you have any questions, I'd be happy to try to help you out. So this is Dr. Berkey signing off. I wish you the best of luck with everything. As always, if you have questions, let me know. Otherwise, good luck, everybody.